So I accidentally made the mistake of not having audio on in my last sprint video. So here I'm going to do it one more time and give a voiceover this time. So this is the Visual Diffs or pdiffs project on the GuideRail SIG, and I'm talking about the work that I did in fall 2016. So the motivations for our particular project are the same as always. The idea is that web developers are self-taught often and project-oriented, and what that means is that they will primarily focus their learning and developing new skills on the particular projects and features that they seek to complete at the current time. And so to that extent, right, existing websites are very rich sources of inspiration, both in terms of designs, but also because they provide contextual designs and contextual implementations of websites in particular contexts. And their problem is that these websites are really hard to inspect, right? So there's a lot of cognitive load that goes on. Cognitive load basically in this context just refers to anything that makes a task really difficult without necessarily improving the learning. So here if we see, here's the example of learners who can reference existing websites. You might say search Stack Overflow CSS tags for like this in a URL, and these are all web questions that people post that are basically asking, how do I do something like this? So this is an example of a parallax effect, right? You find this website that's an example of something you like, and you basically post it and ask everyone, how do I do this? And this is often frequently because learners lack the technical vocabulary necessary to formulate effective search queries, which means that tutorial resources are hard for them to find. So the fundamental kind of idea that we have in need finding is that there's a very high cognitive load involved in reverse engineering existing websites. So here's an example of Airbnb's website. This is the sort of booking search bar that they have. And you basically want to be able, say we want to be able to implement this particular element. So what's happening now is that DevTools is lagging as it does, but I'm going to open up DevTools and inspect this particular element to take a look at what the CSS and the HTML looks like for, this like not very complicated looking entity. Wait for it to load. Yeah, spoiler alert. It's really complicated for what it is. And in particular, there's a lot of like framework generated React crud in here that seems to be not very big of a deal. But when you look at it, so here you see all of these IDs on the divs, and it results in a very difficult to read, sort of a very complex looking DOM tree. So the first sort of barrier that we noticed in learners was that on the element level, they had a really hard time locating the right elements to investigate on the page. But we're going to put that aside for a second. That's sort of one of the lesser barriers in the grand scheme of things, and our tool is really designed to focus on the CSS related problems. So the second problem that we encountered with CSS was once you've selected an element, you can sort of look over onto the other side of the DevTools, and you'll see that DevTools has basically shown you all of the styles that match that particular element, and they're in descending order of specificity. So at the top are the styles that have like the highest CSS specificity calculated by the browser. And so you would expect that all of these properties are going to be sort of roughly ordered according to their relevance, right? But it turns out that learners have a really difficult time picking which rule sets to choose. And the reason you can't just sort of heuristically go with the top ones, like see right now, you would assume that all of these properties are going to be really relevant because they're in the highest specificity rule set. And display table, like disabling that did sort of break the layout a little bit. But if you disable the rest of these, it turns out that nothing happens, or in the case of the last two padding properties, very little happens on the page. So here we have, most of the properties in the most specific CSS rule set can be disabled without any change happening to the page. And the reason for that is that on professional websites, you oftentimes get a lot of this cruft with either third-party frameworks that are imported or standardized style guides for the whole website. And those particular properties aren't necessary for whatever the user wants to implement. And so if you can see how sort of looking at this cascade, it's very confusing to a learner who doesn't understand what they particularly don't understand, like how to filter out the signal from the noise, so to speak. The last challenge that we saw in need finding was that on the property level, and this applies more to when learners are actually taking source from the page and trying to build their own thing themselves. Not sure what I was doing here originally. But basically the idea is that there's a disconnect between what learners believe a property will do and what it actually does. And sometimes how this manifests is I'll type a property. So for example, I could think about the CSS property left. The left property, you would assume, just sort of shifts it to a side. And this is going to be an example of a place where the left property does indeed shift the element. So you can see here that it's moved. But if you find like a different element on the page, so for example, let's try it on this form. Suppose we add a left 50 pixel property here as well. Nothing happens. And so this is what I call an ineffective property, i.e. a property with no effect. And the reason nothing happened in this particular case is because left actually depends on the element being positioned, fixed or absolute or relative, and this element isn't. So there's sort of these hidden dependencies that mess with learners' perceptions of what the behavior or outcome of a property will be. And this is very frustrating for learners who are attempting to replicate source code from professional websites, because they end up spending a lot of time copying properties over to their version that don't end up being relevant, which means it's really difficult to identify again what the crucial lines of code are. So those were sort of our need finding motivations. And the research questions so the high level research question is, how might we decrease the cognitive load of reverse engineering static web designs on existing websites? And again, that speaks to the difficulty of using the inspector. The specific question we focused on for this quarter is, how might we use visual image comparison metrics as a heuristic measurement of the relevance of CSS properties? And in doing so, we can determine which properties are relevant and therefore which properties are not, and we can avoid showing learners these ineffective properties in the inspector. We can just like directly hide them from view in the inspector, which really increases the ability to sort of comprehend everything because there's less cognitive load. So the system we introduced is called ply, and the summary is basically ply does the thing where you toggle properties on and off to see whether they work. That was something we noticed that a lot of novices did in our need finding study, but it was also a very exhaustive process and necessarily sort of time intensive. So the system basically takes as input a URL and element selector. Then it just captures a screenshot of the base page and more or less matches all the styles for the element. We can get rid of some a priori, but here we'll show an example of the next part, which is pretty cool. So we spin up a new instance of Chrome Canary because we do instrument Chrome for this particular system directly, as opposed to using a headless browser like Phantom CSS. Now we're going to start this particular example, which has been preloaded with a website. This website is going to show some cool tooltips, and let's say we want to understand how this tooltip is built. So here you can see on the left side of the screen the sort of like styles being toggled on and off automatically, and on the right you can see these properties being accumulated with the corresponding pdiff impacts. And we're using the, oops, that's an error. We're using the pixel match algorithm put out by Mapbox to perform this sort of perceptual differentiation. And basically all that will happen is we go through all of these properties, and at the end we can see here's like the total number of properties, here are the average diffs, and we can compute sort of a normalized idea of the visual impact of individual properties on the page. But what's interesting is that we can also get the properties that have zero impact on the page. And these just correspond to the ineffective properties that we've found in need finding, that people frequently sort of were the red herrings, so to speak, that people were distracted by when they attempted to identify the crucial source code. So if we go back to the, if we take a look at like what the tool is actually doing, it iterates through the match styles and takes screenshots that it uses here to compute sort of the takes screenshots and then uses the browser to toggle these styles on and off so that we can take a look at what the page looks like before and after they're applied. Here's an example of a different website where we have sort of this like full screen like hamburger menu appear, and it's a little weirdly scaled so it looks big. But basically, here's an example of what the page would look like if we were to disable the background property. So you can see here that you still have sort of this text you can see in the center, but the background property, including both the color and the positioning, and so on and so forth, are gone. And here we can take a look at the diff image. So the red pixels correspond to pixels that differed between the base and the version where the property was removed. And this is going to have a very high pdiff score because there are a lot of red pixels, right? There's a one-to-one correspondence between the score and the visual impact on the page. So that's sort of a summary of how our system works. Again, we are instrumenting Chrome Canary via the remote debugging protocol. This turns out to be pretty significant because a lot of other systems that are do similar things, including Scry by Brian Berg and Andy Ko, as well as the Web Crystal, which was sort of like one of the first big things in this particular space, rely on the computed styles. And computed styles turn out to not be very helpful for this because we would ideally like to be able to first perform this kind of slicing of the program code and using the original source CSS. And second, be able to sort of distinguish between what is and isn't relevant in the inspector. And computed styles just collapses all of the entire cascade into one style that's computed by the browser. But that doesn't help learners know either which parts of the inspector to care about or how to replicate that on their own. So that's why using remote debugging protocol to have browser-level access to style sheets is good. For the study, so the study with people is currently in progress, but we did evaluate this tool as sort of a sanity check on a bunch of different toy examples that constituted like implementations of modern CSS properties. Here's an example of a form where we've sort of created different styles on top of the WebKit basics. And it was very cool to note that even though it's hard to find like good statistics about these examples because they were deliberately not very noisy, the system was able to identify ineffective properties in all of them, and there were very few false positives, meaning properties that were not relevant to the overall outcome, but did have like a big pdiff score for some reason. But it's a little more interesting to think about how this tool works in the context of professional examples, because the utility is really in being able to identify and strip out properties that are ineffective. So let's go back to the Airbnb example we were looking at earlier, right? Suppose we want to implement this search form, which is currently messed up because I had added that 50 pixel left property, so we can disable it now. So using this Airbnb search form here, it looks very complicated. There's a lot of elements in the left side of the tree that go into it, and there's a lot of styles that correspond to each of those elements on the right, and as we've seen, right, we don't even know which ones are pertinent or not to creating this sort of like this three-column like checker thing. It turns out that using the tool, we can reverse engineer out the relevant parts, and it ends up being a much more compact version than what is currently seen in the DOM. And all we do here is sort of rely on our tool apply to notify us of which properties we don't need to care about and just like don't need to bring over. And then we port over everything that is effective, meaning it has like some kind of impact on the DOM. Here we're not even distinguishing at a granular level between a large impact and a small impact. So this is an example of what it looks like when you try to reverse engineer a component using our tool. And it actually works pretty well. So we can take a look at just the HTML and the CSS for a moment. First, we've simplified the HTML drastically. The way we're able to do that with this tool, although that's partially wizarded for now, is that you just go through the elements, and if computing the styles for each of the elements has no impact on the page, then the element doesn't really serve any purpose as far as like the visual impact goes. So you can just use just like the standard algorithm for taking a child, moving it up to a sibling, and then just deleting the original element. Here on the right, we've seen the CSS. And again, this isn't perfectly automatic output. This is sort of stuff I wrote by using the tool. But for example, but all of these lines are directly from the source code, for example. I didn't write any of this originally. And so this is an example of what it would have looked like before. I just sort of consolidated them for ease of reading. But all of this is taken from the tool, and it's a lot less than what we had before. And the output is very good in this case. So there's some weirdness with this search button on the end, but generally speaking, you have this display form that looks pretty closely to the original, but has drastically less CSS. And you can even focus even further on the sort of search button at the end here. So I guess this is just comparing it to the original. But if you want to think about the size of the reduction for, like, say, just the search button, here is an example of a default browser styled button coupled with the version at the bottom is the original button, like just taken from Airbnb's website, and here's the modified button that our tool created with, like, by getting rid of ineffective properties. And on the left here, you can see so here's the CSS at the bottom for the original button, and there's quite a lot of it for a single button. Up top, we have the CSS that was outputted by the tool, getting rid of, by commenting out, all of the ineffective properties. And there's quite a significant number of properties that have been commented out, but as you can see, the modified button still looks pretty closely to the original. And in fact, the only thing that differs significantly is the lack of the border radius, because it didn't produce a significant enough perceptual diff for the system to count it as important. But you can see here that a large number of properties in both this sort of base style, as well as at the bottom here, the styles that would be the highest up in the inspector, i.e. you would assume they'd be the most relevant, a lot of these things have been commented out. And that sort of like goes to show that it can be very misleading to a user who is just looking at the raw inspector output, because it doesn't actually correspond that well to visual impact on the page. Specificity doesn't actually correspond that well to visual impact on the page beyond the obvious, like, don't get overridden part. So here we've seen there's 53% fewer properties just for like a single element, a single button. And this is an example of how we might visualize that to the user. So this is a screenshot of a prototype where you can kind of gray out all of the rules that don't have any relevant properties, coupled with the DOM nodes that you're not focusing on, and then you can highlight properties that are shown to be especially relevant if you're on a page where there's a significant enough variance in the distribution for that to be meaningful. So we've seen that visual diffs are great for detecting ineffective properties, where again, ineffective property means that it doesn't have any real impact on the page. And I don't know what I meant by just putting especially helpful, but it is really helpful for being able to cut down the amount of cruft that you see in the inspector, and decrease the cognitive load for inspection by showing a learner only what is relevant. And the work for them there is much less than even a lot of the other tools right now, because we're able to focus on static web designs, where the visual output that you see on the page is sort of like a direct function of the source code that you would add. So here's an example of what didn't work. The idea is that states are really hard to capture, obviously, through single instance snapshots. So consider a case where you have a button base class with an opacity, say, of 0.5, and we want to add an active class on top of that button that will be triggered at some point, where we'll up the opacity to 1. Using pdiffs, because the opacity 1 overrides the 0.5 and we disable things one at a time, we would say that the 0.5 should not be there, right? And we would get rid of that. However, you don't actually want to get rid of that in the whole style sheet, because that means that all the other buttons that don't have the active class suddenly now have their opacity bumped back to 1. So that's one example. And another instance of when stateful change is hard to capture is with media queries, right? So media queries are, in theory, you can compute the pdiffs for those by just programmatically resizing the browser window to each of those breakpoints. But in practice, it becomes very difficult to do in a computationally efficient manner if you have to test every property at every breakpoint. So currently, that's a limitation for responsive design, which is pretty significant because people do want to learn about that. Another part is that visual diffs are just very sensitive because they're on a pixel-based level. So, for instance, photos, right? If you go to Tumblr, because Tumblr is apparently one of the only examples that our SIG is allowed to use, here you'll see that like oftentimes they have photos as background images. And photos are extremely sensitive to change. So if you shift this even slightly, like what just happened, right? You get a lot of jagged artifacts in the diff image, and therefore an artificially high diff score for what was actually a very small change. Animations, the same way. There was a brief pause at the beginning of this page where the stuff loaded. Animations, interactions, non-deterministic UI. So for example, if you had a widget that showed the date, that would change depending on what day you visited the page on. So you could artificially have a change there. But either way, there are ways to hook into the system. So for example, the way we do test Tumblr is by setting sort of the millisecond timeout before we start the whole process. But because we do want our system to be able to work for any web page, it is somewhat unreasonable to expect a learner to be able to like specify a millisecond timeout for the page that they're on. So although this does exist in a technical standpoint, it's difficult to use for a research and usability standpoint. In terms of what's next, we want to be able to extend this work back to what we were doing originally, which is sort of this overarching goal to build a easier to use inspector. So right now, ply serves as a technique that can be applied to filter the results from any inspector and decrease the amount of stuff that's shown there. It's not as heavily interface dependent because it's more of sort of a technique for minimizing information displayed. In theory also, this technique can be extended to work with any subset of HTML and CSS because those languages are both pretty straightforward declarative and also modular languages. So you can just say, suppose, comment out this range of HTML, what is the effect on the page? If there was like an effect that it's below sort of a certain threshold, then it's safe to get rid of that. That allows you to do a pretty fast and efficient form of automatic program slicing, where you can quickly identify what subset of HTML and CSS is directly responsible for implementing a particular effect using pdiffs. And to sort of sum all of that up, we wanted to think about ways to decrease the amount of cognitive load that a learner has when they are inspecting a website. That will allow us to be able to harness these rich, interactive, professional examples in the same way that tutorials currently offer a very succinct clarity of code, where you only show sort of what's directly relevant. In this case, you can sort of combine the clarity of a tutorial code by showing only the things that contribute directly to some kind of visual outcome, but also combine that with the ability to use a contextual example that has a particular web design effect implemented on a website that you might already be familiar with as an inexperienced developer. Yeah, so thanks for watching. If I can figure out how to be done.